But we do recognize that this is a test for independence. So hang on, I'm pulling up the wrong thing here. And I wanted to make sure, sugar, there we go, that I pull up the key here. So I'll pull it over. And we need to look at, make it a little bit bigger so we can read maybe. The null hypothesis is always that the two variables in question, deafness and eye color in this case, are independent, and that the alternative would be that there is an association or that they are dependent. Either way is okay to say. These are counts. We have to make sure that they we don't know that they're random counts, but we would assume them to be representative, and that the counts are the expected counts, and we've listed them here, are at least all 5. Did you check that condition? How does that condition show up? How do I find those expected counts? We kind of talked about that towards the end of class last time, if you remember. Where on the calculator do they appear? In matrix, which one? Matrix B. You put in your observed values or your observed counts in matrix A, and then in matrix B they show up. If they didn't actually show up there, do you remember how they are found? How is 25.1 found? How is 76.9 found? We talked a little bit about that before. The end of class, if you remember, has to have the same distribution. So this is out of 32. This is out of 98. These were different. So this is 102, and this was 28, right? So 30 out of 32 would be 25.1. Would be you have to have the distributions being the same. But for now, we'll go ahead and look at the, yes. I know, I'm now looking at that going, that's not the same expected-wise as what they give you here. It is okay to use what the calculator gives you. When we get to something, I'm going to show you something the reason I want you to look at how to do it by hand eventually, but that's not going to help us in this case. It's not. That's what I was saying that, and as I was saying it, I'm like, wait a minute. So there's a reason why I'm trying to do this. Let's wait till we get to that problem, and then I'll show you what I'm talking about. But for now, let's just go ahead and just check the condition. Yes, they all are 5. We're fine. Therefore, we can do a chi-squared test for independence. Why is degree of freedom 1? Okay, row minus 1 times column minus 1. Remember that when you have the two variables like that? So 1 times 1 is 1. So the degree of freedom is 1. They went ahead and found, ooh, pretty, the chi-squared test statistic by hand. Remember how we can do that? The observed minus the expected squared divided by your expected, and then you sum them all together. Your calculator should have come up with this value as your chi-squared test statistic automatically. Did it? Exactly? Okay, good. And then the p-value the calculator gave you, could you have found it, though? Try this. Remember how we did the chi-squared CDF? Remember how we drew it and we said, okay, to test it, and it's a right tail probability, 5.87, and we're always looking for that tail when we're doing the p-value here. So it's going to be chi-squared CDF 5.87 to E99. Degree of freedom is 1. I believe that's what you type in. Double check me. Can you type it in for me? Let me see that you did it. Find chi-squared CDF. Go ahead and try it. Is it there? Should be there under distributions, right? Make sure you get the same p-value. Nathan, did it work? It did? Okay. And it gave you 0.015? Same thing? Okay. Just wanted to make sure in case I asked you to draw it or how is it found that you know how to calculate it. The p-value is pretty low. We probably should say some sort of comparison value. So if we would want to go ahead and compare that to 0.05, okay? We call that linkage in the AP Stats world. We're linking it. This is good enough for linkage, okay? Just to say it's low, it's small. Or you can write the comparison, that's fine. And then you're going to actually reject the null hypothesis. And then, therefore, there's evidence to say that they are, in fact, dependent. There is an association between the two variables. Okay? Just wanted to make sure we went through another problem like this for independence before we move on to our final test today. That's exciting. Yes, question. You don't have to do this, but if I ask you on a test to show how the p-value was found, that's how you do it. Chi-squared test, and then the p-value shows up if you do that in the calculator. Yes, but this is the reason behind that. Okay? Does somebody else have a different question? Yes, ma'am. The conditions for any chi-squared test are randomization, and the counts have to be 5. The expected counts have to be 5. And so we don't know random, but we're going to assume representative. And then we checked the expected counts, which they're here, which did show up in our matrix B in our calculator, right? And they were all 5. Okay? Good question. Anything else question-wise here? Yes? Okay, finding what by, this, yes? Yeah, there's definitely, yes, there's a reason. I've got to jog my memory and figure it out. The proportions have to be the same. It's the same thing that we did before last time. I'm just trying to figure out how we come up with those proportions. So give me a minute and I'll think about it and how we can come up with it. But you're right, the proportions are the same. Like 30 to, which proportions is it? Is it 30 out of, hang on. We'll play around with it since we want to figure it out. So let's write these numbers back down again. Right, these counts matter, I believe. And the problem is the 4.9 is not what you want to come up with in terms of the difference. Like, how would you come up with those numbers, right? You can't. No. That's what we're trying to figure out. How does 25.1 come up with? So how did 25.1 come here, and how did 76.9 come here? These are your expected counts, 6.9 and 21.1, assuming the placement of light, dark, meningitis, and other is the same. You figured it out for us, Devin? Yes. Please. Start over. Right? The total of a cell or the total of a row? Okay. So you take 28. Okay. That gives you a percentage. So 28 out of 130 should be the same as 2 out of 32? No. Yes. Yes. That is correct. Okay. Just making sure you were, yes, that is right. So let's there is a reason, yes, by all means, and that's why I said for now. But Kyle, there's going to be a problem, a multiple choice problem that's going to come up. It's going to say, what if you didn't know that, but you knew this? Can you find that? So it's going to come up eventually. So I want you to be able to do it. So it's not that bad. So watch. Okay? 28 out of 130. Type it into your calculator. Give me a proportion. Everybody do it. Okay? Get that? Okay. So now we want this number, okay, to be what out of 32 would give me that same number. So we'll write it this way. What out of 32 is the same as 28 out of 130? Maybe seeing it that way is better. Writing it as a proportion. Yes, Devin? It is a conditional probability. Did you get 6.9? Yes? No? You did not? Okay, she scared me. Okay, I'm sorry, I couldn't understand you. So let's try 25.1. What would the condition, what would the proportion be to figure that one out? Now it would be 102 out of 130 is the same as x over 32. Yes. Double check me that you got 25.1 that way. Did you? We okay with that? That you should have gotten 25.1 this way. To find 76.9, that's going to be 102 out of 130 is what over 98? It is a conditional probability. If you want to think about it from a contingency table, it's the condition that that is the same as the proportion of what you're given. But again, the calculator does give those values to you. But this might come in handy later. Not today, but later. Okay? Any concerns? Not for me, for her. Okay. We're good? Okay, then, let's look at the answers to the homework. We are going to, let me go ahead and, this is going to be oh, it's not up there. Interesting. All right, so the answers to the homework, you guys, I'm only going to look at the even problems because the odds were in the back of the book. So you guys had to do problem number 2 because you were asked to tell me what kind of a chi-squared test it was. And we're going to do some practice with that, but with all of the tests today, what test is it? And we're going to practice that a little bit. And you guys are going to have a quiz on Wednesday, very much like what you see here today. So let's go ahead and look at number 2. Let me read those answers first. You ready? Number 2. A was chi-squared goodness of fit test. B was, I don't know, some other test because it's not chi-squared. 2B was not chi-squared because they weren't counts. They were quantitative. They were measurable. 2C was chi-squared test of independence. Okay? And then you guys had to do 4. Oh, I'm sorry, question.
How is C independent?
Okay, let's look at it. So C says, a student wants to find out whether political leaning, liberal, moderate, or conservative is related to choice of major. So I have 2 different variables. I have political standing and choice of major, and are they related to one another would be an independent situation. Okay? All right, number 4. Nothing. It's not chi-squared. Because it was you were given quantitative or measurable data, so it wasn't counts. All right, ready? 4A, the answer was 31.8 brown, 10.6 green, 10.6 blue, 10.6 orange, and 21.2 yellow, and 21.2 red. Yes? Part B was goodness of fit chi-squared test. C, the the null hypothesis was the distribution of M&Ms is the same as specified by the company. And the alternative was that it's different than what the company suggests. D, they were counted. The data was counted. They were, the M&Ms are in the bag are assumed to be representative, or they're at least randomized, hopefully. We'll say they're representative. And then E, the expected counts, all that we did in Part A were all larger than 5. So that was good. There were 5 degrees of freedom for Part E. And Part F, the test statistic was 9.314. The p-value was 0.0972, which was too high. When you put that linkage there, it's higher than 0.05. Therefore, we failed to reject the null hypothesis. Therefore, the distribution is the same as we don't have evidence to say it's different. Okay. And then you guys had to do 26. And I did grade problem 26 as the extra credit one today. I was looking for the p-value in 26. It was that Titanic situation. The p-value, first of all, the test statistic in 26 was 453.476. Did y'all get that? Yeah. Pretty high, right? The p-value was essentially 0. I think the calculator even told you it was 0. Yeah. Did it? Yeah. It was just so close to 0 that it wasn't going to give you, I mean, obviously we know the probability of something being 0 would be never happening. Be approximately 0, right? We would say that. And then because it's such a low, we would reject the null, and we have really strong evidence, right, to say that there is an association between survival rate and gender on the Titanic. Okay? A little bit different than the class ticket we talked about last time. It was strictly just gender. It kind of makes sense historically because there really weren't many females working on the ship, right? So, okay. Any questions on your homework? Nope. All right then. We're going to look at one last test. So you want to write these pieces of information down. And you are going to open your textbook to page 657. So go ahead and look at page 657. I asked you to grab a textbook off the desk first. If you would do that for me. 657. Thank you, Charles. All right, so the last test that we're going to do is called the LinRegTTest, and it's basically being able to decide whether or not two variables have an association, but their kinds of variables are different. If two variables have an association that are categorical, it's going to be a chi-squared test, correct? Categorical data is all chi-squared. What kind of data do we talk about having a regression, a linear regression? Not categorical, but quantitative or measurable data. It's bivariate. The two types of data, the kinds of variables are going to be measurable quantitative data. Okay? So if I have two variables in which I can measure that I'm trying to find an association between, then we're going to do a LinRegTTest. Do you remember back, months ago, when we looked at correlation and we said correlation doesn't prove causation? But a LinRegTTest can say that one and the other have an association, which is kind of interesting, okay? So it is the one hypothesis test. When you have two quantitative variables, you can show that there is an association between them by doing this test, okay? You can't say one causes the other to happen without an experiment. Experimental design is it's a good experiment. It's the only way that that can happen, but you can say there is an association between them. Exactly. Okay? When you have qualitative data, like we did with chi-squared test, we're talking about a contingency table, and we're looking at counts. When with a LinRegTTest, we're talking about quantitative data, and we're looking at a scatter plot of that data. The null and alternative hypotheses are always written this way. I love that I can say always on these last few tests. It's kind of exciting, okay? This beta 1, okay, this capital beta stands for the slope, okay? Remember how when we talk about, it's the slope of the population, okay? Remember when we talked about slope when we wrote it, that's just Miss Ellis. When we wrote it back with the regression before, it was just B1 was like the lowercase b, and B0 was the y-intercept, I think. Do you remember that? So this is just talking about the population parameter. The slope is 0. There's no association. That just means it's scattered around. There's really no association. If there is a line of best fit that's going to fit the data, and it is in fact linear, we would say the slope would have a positive or a negative association. The slope is going to have a non-zero slope.
So if they give us a scatter plot, or they give us data
that is quantitative, then you know to do this test. Yes. And in a few minutes, we're going to look at all the tests put together and which test do I use and when. Okay, and that's the quiz you're going to have on Wednesday. Okay, but here's some notable things with this LinRegTTest. One, we've already decided that what kind of data is it? Quantitative data, and you have to have how many variables? 2 variables, right? Okay, it's bivariate. You know you have your hypotheses are always written this way because we're talking about the slope of is either going to be 0 or it's not going to be 0. We're not going to necessarily say greater than or less than. We're just going to say it's not 0. So it's a two-tailed test. I'm not down there yet. We're going to get there. I'm not there yet. Okay? So hypotheses are here. The degree of freedom is different. It's always been rho minus 1 or times column minus 1, or the t-test is just the degree, is the sample size minus 1, right? The degree of freedom with the LinRegTTest is the only one in which it's n minus 2. Okay, so that's kind of an important notable, something to know that's different. Okay? And it's still the sample size. And in order for it to be bivariate data, the sample size have to be the same size, right? Because you have to be matched. So you can graph the point. It has to have an x and it has to have a y. All right, so it's just a sample size minus 2. Now, to answer Zachary's question, okay, this is the test statistic formula. Okay, you are in fact finding the slope divided by the standard error. Okay, so you're going to be looking at a slope of a line and the standard error of that line. Almost always you'll be given a computer printout of the data, which is why having you look at, wow, that was cool, page 657. Okay, on this page you have a computer printout and you can look and see what kinds of information that we'll need. Okay? So, why are we subtracting 0? Well, because that is the claim. When we think about a regular t-test, it's your mean minus the population mean, right? It's x bar minus mu. Well, mu, we don't have a mu. We're talking about 0. The slope is 0. That's the claim. Okay? So that's the formula for the test statistic, and then you're going to treat it very much like you would any other time. You're going to do your TCDF, you're going to graph it, and you're going to do very much, whoa, that's kind of fun. You're going to graph, so it becomes a regular t-test, okay, where you have 0 in the middle, and you put your test statistic, I don't know where, and you're going to go, since it's going to be two-tailed. Why is it two-tailed, by the way? Because it's not equal to in the alternative, right? So we know it's a two-tailed test. And you're going to find a p-value, and it needs to be small, and then we can reject or null. So everything's really the same, except for the kind of data we're looking at. Okay? Now, as far as conditions go, hopefully they're listed here. If not, does anyone have their stapled 2 pieces of paper that I gave you that had all the formulas and conditions somewhere handy that I could borrow for a second? Sorry, Devin had it right here, so I'll just look at it. The LinRegTTest, is it even in here? Yes. Okay. It's the last one. They're calling it the regression slope test. I've never heard it called that, but that's okay. But that's the test here. And there are 4 conditions, but I believe they are very much the same as the test that we've done before. That's me, sorry. I had to turn my phone on in case the nurse called me back. So are they going to be independent? Is there a linear relationship? Because you really want to look at the scatter plot and see if it's linear, okay? The standard deviation is constant. What does that mean? If we look at the graph, what is a standard deviation? Variation from the center, right? Okay, so if we're looking at, we want to make sure that the data is linear, that it's spread roughly about the line of best fit. We have some above, some below, right? And what was the last condition? Read it for me. Okay, so what does that mean? Response. Is that your X or your Y? Your Y variable is going to be normally distributed. Okay, so there are 4 conditions. I will say I hate to say the word never, but I personally have never seen them ask you to check the conditions on a LinRegTTest, okay, on the AP exam, which is why we're kind of breezing through it a little bit. The only thing I've ever really seen is for you to interpret a t-value, for you to look at a slope, that kind of thing, but nothing where you're really too much concerned about the conditions, okay? So we're going to, I'm telling you what they are. They're there, but hopefully you won't ever have to deal with them, okay? I'd like us to look at the page 657 if we could, and I want us to kind of take note of what information do we need from this printout. If you look at the notables and things that we need to know, we really need to know the sample size. I'm going to highlight them in purple. Oh, okay, maybe not. We need the sample size, right? We need the, why did I choose that color? We need the sample size. We need this number, and we need this number. Can you find those on page 657 for me? Because that's the information you would need to pull out of the output there. So do you see B1? Okay. Notice what it's underneath, because sometimes the printouts look a little bit different from there to there, but it's next to, it's not the constant variable, it's the other one. The constant variable is always going to be your y-intercept, okay? And then your, whatever the other, they always put it in context. Here it's waste. I don't know what the other variable would be, but whatever the context is, that's the coefficient that we'd be looking at, is going to be your slope. So in this case, it's 1.7 about. Do you see that? Okay. Now, the other piece of information you need is the standard error that's associated with that same variable, and it should be right next to it. Is it here? Yeah, if you look at it, it's right next to it. So in this case, it'd be 0.0743. No. Okay, on a LinRegTTest, the only time I've ever seen it, you were given this information. Okay? So, let's go ahead and find the test statistic that's associated using this formula here with this page. So we're going to say the test statistic would be the slope minus 0 divided by the standard error of the slope, which there are formulas for this, by the way. Do you remember, like if you look on your regular formula sheet, wasn't there a slope formula or to find the standard error? You could use your correlation. We did this like months ago. It's on that, I think it's the middle column of our formula sheet? Or the left-hand side? The left-hand side? Okay. But those formulas are, this can be calculated. Okay, just so you know. All right, so the B1 when we got was 1.7 was our slope. The standard error that we found here is 0.0743. So what is the test statistic that they found here? Well, that's also in the printout. Doesn't always give it to you, though. So I'm just telling you that I have seen computer printouts where, like, the t-ratio is not there. Okay? So you do need to know that it is the slope divided by its standard error. Just because sometimes those last couple columns aren't there. It'll give you what you need, but you might not find it. It should be about that, though, is it? If you divide them? Something like that. So if we wanted to find the p-value that's associated with this case, you with me so far? What I'm doing? And we're just going to calculate that. We should get a pretty small p-value, I think. Let's see. So we're going to do two of them because it's two-tailed. We're going to do TCDF, and we're going to say 22.9 to E99. The degree of freedom was, what was the sample size, by the way, here? 250, so 248 was our degree of freedom, because it is minus 2, and we'll paste. And so we get, ooh, not quite 0, but gosh, I'm not writing that. Okay? That E negative 63 does mean 63 decimal places. So this is what I would, the p-value is approximately 0. Okay? Right? So linkage, what are we going to say? That it's small or large? Very small. Okay, very small. So we're going to say it's very small or that it's less than 0.05. Therefore, we're going to reject the null. And what would we say in the context of the problem here? We're going to reject the null. There is an association between, and then the variables in context here were, I don't know, let's go back and look at it. Waist size and body fat. That kind of makes sense, right? I don't know very many people with a small waist size that have a really large body fat, or vice versa. So it kind of makes sense. Okay? That's all I'm really going to do with you on LinRegTTests, okay? Is can you look at a computer printout and pull out the information, and can you come up with a hypothesis test and what it would be. That's really it. Okay? What I think I'd like to spend the rest of class today looking at, we'll worry about the themes on Wednesday, is you're going to have a quiz next class very similar to this one, what I'm about to hand you. It's almost identical to different situations. So I have given you a bunch of situations A through H, and I'm asking you to be able, these are the situations, by the way. I'm asking you to fill out the chart that you'll see on the second page that I'm handing out to you. You're going to decide what test it is. You're going to decide what test statistic I need to use, and the degree of freedom if it applies. Okay? So you'll see when I hand this to you what I'm asking you to do. No, everyone gets the 2. Everyone gets 2. So to reiterate, next Wednesday you're going to have a quiz. You'll need some more assessments after that last quiz, by the way. Once Tanner takes his, he's going to do that here in a couple minutes. I'll give you your quizzes back that you had last time, and we'll go over them. But on this here, we have A through H. These are all different situations, and you're going to fill out, oops, not that chart. Hang on, what chart was it? Where'd it go? There should be a chart somewhere. I'm sad, where'd it go? All right, well, I'll figure it out. Anyway, you're going to take these situations, and you're going to fill out the chart on the next page, okay? You're going to decide for A, is it going to be, in the type column, you're going to fill a 1 through 9. Does that make sense, what I'm asking you? Okay. So match up which test. Once you figure out what test it is, you're going to tell me, am I using a test statistic is Z, a T, or a chi-squared? And then if the degree of freedom applies, it only applies in T's and chi-squareds, right? So if it doesn't apply, just put a dash. It doesn't apply. But I'm going to give you a few minutes to try this on your own. You can talk to some people at your table, kind of work through it a little bit, and then we'll go over it towards the end. All right, so let's go ahead and go over the answers to this problem. I have them kind of over here off to the side. It's H, scenario H, that caused some difficulty that could have been more than one possible answer. So let's go through and check your answers. And let's see how well we did. Okay, so if you look at scenario A, we are looking at a situation where we're talking about 2 different measurable quantitative data, 2 different variables, which means, that if it's related to, it's either going to be a chi-squared or a linear reg test, right? LinRegTTest, it's one of the 2. Since they're quantitative variables, we know it's LinRegTTest. Question about why number 1 is 9. Okay with why it's a test statistic is a T, and why the degree of freedom is 58. We're good? All right. Any of those up there that you got wrong that you're not sure why? We'll talk about H in a minute. Devin. A, B, C, D, E, F, G, C. Okay, let's look at C. Says an orthodontist wonders if soda in the diet may be a factor in loose cement on children's braces. She checks the cement bonds of 40 randomly selected patients who do not drink soda, and 40 for those who drink soda. So we have two independent samples, those who do and those that don't. So it's a two-sample t-test. Hang on. Well, that's not really clear, is it? And I kind of agree with you in that particular problem. But it could be quantitative because you could talk about how much it loosens and that kind of thing. I don't think it was a yes or, oh no, actually no. Well, that's not true. I see what you're saying. Shh. I'm sorry, say it again.
Like the null would be like soda, drink it, or however that is, soda.
So what did you say it was? Oh, chi-square test of independence? Could be if the question was asked yes or no, is the cement loosened? And I'm not so sure that the question was clear that that's how it was, right? But we do it wouldn't be independence though. It's two different samples specifically. And so let's read through that again. Let me just make sure I'm clear in my head. She checks 40 who do and 40 who don't. So that's two independent samples. So it could be a goodness fit chi-squared because that's when you're talking about two independent samples. It wouldn't be independent. I understand that, but they're independent samples. What you either do or you don't, right? So it's definitely not going to be independence, the way that that's worded. I see where you could have said that does one affect the other is kind of what you're thinking, right? That one's I agree, that one's got a little bit of a gray area. I'm just going by what the book says, but his question is because just because it's, well, first he's thinking that it could be chi-squared test for independence because it could have been like a contingency table where it's yes or no, my braces are loosened, or yes or no, I drink soda is kind of what he's asking. But I don't think that's the way it's proposed. It's proposed as two independent samples. From those two independent samples, he's asking the question. So that's a little bit different. You're not trying to show an association between the two variables. You're trying to show that within the two variables, they're loosened. I don't know if that makes any more sense. I don't know if I've confused you more or not. We'll come back to that one, though, if we need to. Any others besides C?
Degree of freedom for E and G.
Okay, so E. Let's look at what E is. That one was just a regular old chi-squared for E, right? It's a homogeneity situation. You're trying to see whether or not, well, you have one, let's see, hang on. You have Australia and, oh, I'm looking at the wrong one, sorry, E. Health professionals, selected random 4 major hospitals to see whether or not, okay, so yeah, you're trying to see if it's homogeneous, right? So the 4 different hospitals, are they the same? So that is a chi-squared test for homogeneity, which was what? Is that 7? Yes, okay, good. And then the degree of freedom is, why is it 9? Is that what you're asking me? Okay, so it's 4 minus 1 times 1, 2, 3, 4, 5. There's 2 categories, right? Because homogeneity, you have 2. It's row minus 1 times column minus 1. Okay? Okay? Any others besides that one? Let's talk about H for a second, if we could. Now, it says here on H that 6% of the 473 men, they had been adopted compared to 4% of the women. Different sample sizes. Does it indicate a difference between adoption rates of females and males? Now, I agree that to me, that's a difference of a 2 sample proportion, right? I think 2 makes the most sense. But I could have taken those proportions and made them into counts and created a contingency table for them. That's why 7 or 8 could have been used, okay? So when you have proportions, it is possible to do a chi-squared test, but you have to go from the proportions or from the percentages and create counts based on that, okay? So that's why 7 or 8 is possible, but I think in this case, two proportion z-test makes the most sense. All right, that's why H. A two proportion z-test makes the most sense to me, but you can go from proportions to counts. You just have to create those counts. Okay? All right, so I wanted to give this to you. I want you to give you some practice to work on this, and there is a website, and you need to write it down. I will link it. Hopefully, I'll have time to do this right now and put it in. Oh, it's a big, long thing. I'm going to put the link. I'm going to copy it and put it on School Fusion. Does that sound good? But I'm going to show you what happens, maybe, what this looks like. This is an actual practice where it comes up with different scenarios, and you're asked to figure out what happens. So let me kind of copy it real quick and paste it into a browser so you're going to see what it looks like. So it's called, this guy named Larry Green is the one who did it. If you go to statistics, we want to, hopefully it's still there. Uh-oh, hopefully it didn't move. Basic math. No, we want to hypothesis test is I think what it is. Hypothesis test for a mean, comprehensive. I think it's practice classifying statistics problems. And this is what it is, okay? So we want to select the categories for what the tests that we've done. We have done all of them except for the ANOVA test. Some statistics courses do that, but we don't need to do all of them except for that one. By the way, prediction for a single value of y for a fixed x is the LinRegTTest. It's just the way they said it. Oh, paired, we've done paired. Okay, so this is just the LinRegTTest right here. Okay, so all of them except for ANOVA, and we'll submit. And then it's going to ask you a question, and you're going to have to pick what test it is. And it does do confidence intervals, so you'll have to know when a confidence interval is appropriate versus when a hypothesis test is appropriate. And I'm just going to randomly pick one. It's probably going to be wrong. I just picked it, and it says, no, and it gives you a frowny face and says try again. So you just can kind of pick them. Hang on, I'm not sure what it, I think it comes, I don't know. Anyway, you're allowed to retry again, I think. So you want to try and keep playing with it. But I'll copy and paste that onto School Fusion. But that's a good practice for the quiz that you're going to have on Wednesday. Okay? So you're going to do something almost identical to this on Wednesday, but this is your practice. And that's your homework, is just to practice and study.